In this video, we're going to solve this problem using Abacus, the finite element commercial software. The problem consists of a bar that is fixed at this end. It has a length of 20 inches. It has a concentrated force being applied at the length of 50 pounds. It has a body force that changes throughout the length, whose magnitude is 3x. Remember that the units of a body force in 1D must be equal to pound per inch. So that means that this has a unit of pounds per inch squared. So when you multiply times x, will give you a units of pound per inch. And it's going to change throughout the length. The cross-sectional area is 5 inches squared. The elastic modulus is 29 million psi, which is the elastic modulus of steel. Now we're going to solve this problem following two approaches. The first approach, we're going to use 4 linear elements. So these are the 2-noded elements, and we're going to use 5 nodes for 4 linear elements. And on the second approach, we're going to use 2 quadratic elements. We're still going to use those same 5 nodes, but now we can only use 2 quadratic elements because we have 3 nodes per element. So let's open Abacus. So if you go to Abacus, be sure to select Abacus Standard, and we're going to create a part. So we're going to work on 2D space, and we have a kind of a wire type problem. So we're going to say 2D wire deformable, and this is just an approximation size for our grid. So we're going to say it's 100. Then here, let's select the first node at 0, 0, and then let's select our second node at 20, 0. And then we say done. Then we proceed to create the material. So within the material, we're gonna call it steel. Then we're gonna define the elastic properties, which are 29 e to the 6 and Poisson ratio, although not needed for bar problems, but we have to specify it for Abacus. We're gonna say 0.3. Then we're gonna go create a section, and we're gonna say it's a beam, it's a truss type, and it's gonna have a cross-sectional area of 5 according to our problem. And then we're gonna assign this section to our problem through section assignment. And we already have our bar. Then we're gonna proceed to assembly, and we're gonna select that part. And here you can choose to mesh it on the part on the instance. I always prefer to mesh it on instance, and put here OK. Then we go to meshing. We have to select an approximate size for our elements. So we said that we wanted 5 nodes, 4 elements. So 20 divided by 4, that would be 5. So I want elements of length 5. And here I'll have 4 elements. I say done. Now I need to select my element type. And for that, I'll use truss. And now here is where I make the decision between using linear or quadratic elements. So linear are my 2-noded linear 2D trusses, while quadratic will be the 3-noded quadratic trusses. In this case, we want to use the linear, and it will follow the linear interpolation. So we say OK. I still haven't meshed, so I have to click on this bottom and say mesh yes. We can see the node numbers and the element numbers by selecting these 2 options. So here you have in orange the element numbers 1, 2, 3, 4, and the node numbers in magenta 1, 2, 3, 4, 5. Then we can proceed to create a step. This step, it's going to be static. So we're going to put static. And here I apply my concentrated load and body force. First, let's start by defining the boundary conditions, which in this case, since I'm in a 1D, I just need to define that there's not going to be any displacement here. And then I apply my loads. So I'm going to have a concentrated force of 50 pounds acting in the positive x direction. And then I'm going to have a body force throughout the whole length. So I select the whole length. And the magnitude is going to be 3 times x squared. Now, uniform will only apply 3 throughout the whole length, but if you want to apply a different magnitude, then you need to select an expression here, creating an analytical field. You say continue, and here you can make that function of x. So you select this x here, and then within the distribution, I apply the analytical field that I just created. So the body force is going to be 3 times the analytical field, which is x. And here you can see how it changes as a function of x. So the body force is very small here, and then it goes all the way to 3 times 20. So it will be 60 here at the length. And if I didn't make a mistake, this should now be able to run. So I create the first one here with linear elements. And then I visualize the results. So let's start by selecting the displacement. And let me actually move a little bit so you can visualize what's happening. So you can see here that the displacement changes along x, even within an element. So this is the first element, and you see how within that first element, there's some variation in displacement. Within the second element, within this third element, and within this fourth element. Obviously, the magnitude increases as you move away from the fixed node. But now let's look at the stresses. So look at this stresses as 1, which is your axial stress. And you see that you have more or less constant value within the first element. And you should have a constant values between the second, third, and fourth element. Actually, let me refine and AVAX actually applies a specific unknown system to color the results, but we can report the results. Now let's repeat the problem, but now let's use quadratic elements. And so let's delete the whole mesh. And now let's specify that our size for the elements, it's going to be equal to 10. So we're going to have one element within here and one element within here. And now we select quadratic elements. So that will be quadratic here, truss quadratic. So that means 3-noded trusses. And then now we say mesh. So you see here I have 2 elements, 1, 2, and then I have 3 nodes within each element. So we don't need to change the load, we just need to resubmit the job. But in this case, let me call it quadratic elements. I need not to have any spaces within my name. And now let me submit it. The job has completed, so I can go visualize the results. And now here, let's look at the displacements. And let me make this zoom. But now let's look at the stresses. And the stresses should vary as a function of x. Now let's compare the results between the 1D and 2D. So you see that the maximum stress here is 6.1, while the maximum stress within the linear elements is 5.913. In terms of displacements, the maximum is 2.78 in the linear elements, while in the quadratic elements, it's 2.655. So you can see here the difference in the approximations due to the selection of different elements.